Okay, so this is the start of a new unit. So exciting. And actually, what's most exciting about it is not the fact that it's just a new unit, but this is kind of the point where we start to get into the real big stuff of AP chemistry. So from here on out, everything that we see is really going to start to encompass lots of different concepts, lots of different ideas. And you're going to start to see the way that everything really weaves together. So, this is about thermochemistry. And thermochemistry, if you kind of, break down the word itself, you can see the prefix thermo in there. So hopefully you get something that, we're dealing with something like temperature or heat, and of course the chemistry component to that. You'll notice the parentheses, they say from the Ebbing text. So this is from the textbook pages that I've copied for you. So this is meant to be an introduction to both thermochemistry and something called thermodynamics, and we will talk about, as it says at the bottom there, energy and heat also. So here we go. First off, chemical reactions come in two different types. They are either going to produce heat or they're going to absorb heat. And there are two words that you have to be very clear about pretty much starting now. So the first word is endothermic. So, like endo, inside, heat on the inside, or temperature on the inside. These are reactions that will absorb heat energy. Whereas the flip side of that would be exothermic. Exo means to give off heat. And so when you think about these two reactions, usually the exothermic one is the one that makes total and complete sense. If a reaction gives off heat, imagine you were holding the beaker in your hand, it would actually feel hot to the touch, or it would warm up as the reaction goes about. Whereas endothermic is actually opposite. It's actually pulling heat energy out of the environment, and that actually creates a cooling effect. Two really easy examples of endothermic and exothermic. Um, Endothermic reactions occur in those chemical cold packs. If you're in sports or anything, you pull one out of the med kit and you just start crunching the bag all up, and then pretty soon it is a cold pack, and that's a chemical reaction that's endothermic, and it produces the feeling of cold. Whereas exothermic reactions are very common in the hot hands, those things that you probably use during football season. And remember, you take them out of the package and then you just shake it all around, and then the oxygen from the air gets in, does the chemical reaction, and then gives off the heat that keeps you toasty warm throughout the whole football game. Yay! Okay, so thermodynamics is the broader of the terms that we're going to talk about today, or the disciplines, I guess. Thermodynamics is actually a branch of science, and it deals with relationships between heat and energy, and in several different forms. Thermochemistry, on the other hand, is sort of a branch of thermodynamics. So we're kind of getting a little bit smaller, and it's specifically concerned with what you see there in red, the quantity of heat that's absorbed or evolved during a chemical reaction. And you'll want to start to get comfortable with the word evolved, meaning that heat will be given off into the environment. And again, that would be similar to saying that it is exothermic. So if heat is absorbed, it's an endothermic reaction. And if heat is evolved, then it's an exothermic reaction. Okay, just to kind of continue, specifically, we will be focusing really, really heavily on thermochemistry, and we're going to be working with a couple different things. Number one, heat that's involved or energy required, which tend to be sort of similar in the breaking of bonds. So we'll see some things later on in this unit about breaking bonds and what kind of energy is required for that. And then, if you were given a set of chemical reactions, you can actually determine a total amount of heat that is either absorbed or evolved, and that's something that'll be coming up in a little while. It's called Hess's Law. So you get a set of reactions instead of just one. So little extra info. Couple new terminology words that you need to know about as we move forward, specifically because you're going to see some of these in homework problems, and I want you to be clear about what they're talking about. There's something called the thermodynamic system. And that is basically whatever you're studying. It's whatever reaction you're doing. To put it in the easiest possible terms, it's what's reacting in the beaker. That's your system. Whereas your thermodynamic surroundings is anything that's in the vicinity of the system. So generally speaking, we consider that to be like an air temperature. So for instance, if you are going to produce heat, evolve heat in an exothermic reaction, but the air temperature around the beaker is already incredibly hot, it won't have the easiest time doing the reaction because it's trying to pump heat into something that's already hot. But if this hot reaction, we're trying to pump heat into a cool environment, then it can have a much greater impact. So sometimes the surroundings can impact the favorability of your reactions, essentially is what we're talking about. So generally speaking, though, as we move forward, we will be dealing with the thermodynamic system. All the calculations deal with the actual reaction in the system. Ooh, look at that. Okay, we'll just bring all this in. So this is all stuff that really should be reviewed when we've talked about heat and different things like that before. So heat, remember, cold doesn't exist. Cold is really just the absence of heat. And so when we talk about heat, it's energy that's flowing into or out of a system, and it's due to a difference between the temperatures of that system and those surroundings, kind of like we were just talking about. So heat flows into a system, and the energy in the substance or the energy in the system is increased. And we talked in great depth when we were talking about gases, about kinetic molecular theory, and that's what describes the flow of heat and the transfer of heat. And in fact, as we kind of dive into the kinetic molecular theory, or the KMT as I like to call it, we also learned a lot about how particles and particle interactions really matter here. So when heat is applied to particles, the result is an increase in kinetic energy. They start moving incredibly fast. And the faster the particles move, they begin to collide with other particles, slower moving particles, and they begin to transfer that kinetic energy. And so pretty soon, and I always think of this as like bumper cars or even pool balls. If you have one going really fast and it's hitting one that's relatively stationary, it will cause a transfer of kinetic energy to the particle that wasn't moving very fast. So if you give it enough time, overall they will end up having the same average speed or the same kinetic energy, which creates the same thermal energy throughout the system. But it's just something that takes time. You probably are aware that you don't just apply heat to something and then voila, the whole thing is at the right temperature. You know, it takes time to get all those particles to move around, collide, and impact each other. The big key idea here, though, is that thermal energy transfer occurs through the transfer of kinetic energy. If you understand that, then you pretty much have the whole idea of kinetic molecular theory down pat anyway. But it is also important to remind you that when you're talking about increasing kinetic energy and making particles collide, remember it's particle collisions that cause pressure. So when we talked about kinetic molecular theory, we did a whole lot of discussion about how it's a progression of thought. So you've got increases in kinetic energy. I'm sorry, you have the addition of heat, and then the increase in kinetic energy, and then you increase the amount of collisions, and then that in turn will increase pressure. So remember that thought process. Okay, another thing that's really important to mention is that a lot of people tend to think that heat and temperature are the same thing. And that's partly because just of the way it's used in the English language. But think about it in terms of chemistry. Heat and temperature are not the same thing. In fact, heat creates the temperature. Temperature is proportional to kinetic energy. So the faster the kinetic energy, or the faster the molecules are moving, the more kinetic energy they have, and the higher the temperature will be. So what actually happens when we think about heat creating temperature, just read it along with me. Heat will increase a compound's internal energy, which is the movement of subatomic particles. So we're actually talking about protons and electrons and neutrons and everything, which in turn increases the average kinetic energy of the molecules. The resulting kinetic energy is then transferred to all the molecules within the sample, which results in a temperature increase. So it's exactly what we just said on the previous slide about how the advent of heat, or the addition of heat, relates to the kinetic energy, which then relates to the temperature. And another fun fact, I know that you're just dying for fun facts, the given amount of heat, or a given amount of heat, will raise the temperature of a sample in direct proportion to a sample's size. What that means is if I have X amount of heat, but a sample that's teeny tiny, then I'm going to raise the sample's temperature probably significantly. But if I have X amount of heat and a gigantic amount of sample, then that same amount of heat will not increase the temperature of the sample in the same way because there's just so many more particles. So, fun fact, yippee. Okay, how do we measure heat? The calorie, as it says here in blue, is going to be one of the ways that heat is going to be measured. In fact, joules and kilojoules are the ones that we use most often, but we always like to throw in a little bit of a monkey wrench. So why would we just give you joules and kilojoules all the time? Of course we wouldn't, because sometimes we want to make you convert. And in fact, the calorie is kind of a really interesting thing. I'll tell you a little bit more about it in just one second. But the definition of a calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 Celsius degree. So it's a very specific definition, definitely. But then that energy amount can be measured, and then that's how many calories you would have. It's abbreviated with a lowercase CAL. It is not an SI unit. In fact, the joules is the SI unit, which is one of the reasons why we tend to work in joules in calculations. And the conversion factor is as shown in red. 1 calorie equals 4.184 joules. So if you're given calories, you'll have to do the conversion, and then you can actually do the mathematical problem that you would be asked to do after that. So another fun fact, in terms of calories, when we think of calorie, we usually think of food calories. And it's kind of interesting, the way that they initially used to determine calorie content in food is they would actually burn the food, like burn it to a crisp until it was like ashes, and they would just determine how much energy that food burning gave off, and then that would be the calorie amount of that food. I know it's a little bit more sophisticated nowadays, but that was the original method of basically determining calories in food. So, kind of a nifty thing. Look into it a little more if you want. So the final slide of the day is going to be the utilization of this really, really fancy conversion factor that I've just offered you. So here I'm asking you to convert 1.1 times 10 to the negative 17th joules into calories. So just think about dimensional analysis, normal old conversions. Go ahead and pause the video and try it, and then I'll show you the answer. Okay, and survey says your answer is 2.7 times 10 to the negative 18th calories. So as you can see, the 1 calorie over 4.184 joules, so that the joules will cancel, leaving you with calories, and ta-da, you've done it. So that's it for today. A lot of background information, and we'll pick this up in class and see what kind of questions you guys have. See you later. Bye.